Hello to everyone, welcome back. We are continuing the unit 2 of AI. Today's class we are going to discuss about uninformed search methods. Search strategies in AI are classified broadly, like as shown in this figure. They are search strategies, that is, search technologies, overall classified into two major techniques. We are blind and heuristic. In blind search, there are two types again: depth first search, DFS; breadth first search, BFS. And again, in a heuristic search, there are several types. One is a hill climbing search, best first search, greedy search, and A-star search. These are the types of search algorithms popularly that are available here. And if you take a search strategies, blind search, traversing the search space until the goal node is found, might be doing exhaustive search. Techniques could be depth first search, breadth first search, uniform curve search, depth limited search. It guarantees a solution. If you take a heuristic search process, takes place by traversing search space in applied rules. That is, if you know some information about the destination or goal state. Techniques are generate and test, best for search, A-star algorithm. There is no guarantee solution that can be found in this type of heuristic search. And important terms that are involved in searching algorithms are search space, initial state, goal state, problem space, searching strategy, search tree. What is search space is possible conditions and solutions. All kind of possible states and its solutions. Initial state is means a state where the searching process actually started. Goal state is the ultimate aim of searching process, the end state. And the problem space is what to solve. What is your problem actually? That is problem space. Searching strategy is strategy for controlling the search. Any searching algorithms you can use to find your searching techniques. And a search tree. A tree representation of search space showing possible solutions from initial state. It is basically a representation of search space in terms of a tree. If we look into depth first search, in detail we'll discuss about depth first search, DFS. If we consider depth first search, it is based on stack data structure and it follows the fringe of last and first out queue. That is, put success as at front. So if you take this example, this is a tree that has been given here and the initial node will be A. And after the initial node, and it will traverse from the next branch. In the next branch, it is having two types of node, left and right. On left side you have B and right side you have a C, and both B and C will be explored. That is, first B left side node and then C will be explored. Then only in the depth of the search techniques. That is, for A node, first A will be explored and A's children are B and C. Because it is a depth first search, it will go deeper into one branch, deeper and deeper into one branch side. So after A's children B and C are explored, the left side node is B, and as B's children will be further explored to its last depth. Okay, before exploring the next branch, that is C, next child node C. So now the B will be explored. After B, what will happen is B's children are D and E. For D and E, according to depth, it has to go to the left side node D first before exploring the node E. So it will explore only D until all the children of D is being explored. Then only this E will be explored. E will not be explored until all children of D has been explored. So after D is explored, G's children are what? H and I will be expanded. So in H and I, what is the depth of a D? First depth of a D, it is H on left hand side node. So H will be expanded first, then only it goes to I. So what will happen if I is the goal state or H is the goal state, then the searching will be stopped here. So it follows the path from A, B, D and H. This is called as depth first search. If we discuss more into about depth first search is an algorithm for traversing or a searching tree or a graph data structure. The algorithm starts at the root node, selecting some arbitrary node as the root node in the case of a graph, and explore all as far as possible along each branch before backtracking. Depth first search algorithm starts with the initial node of the graph G and then goes to deeper and deeper until the goals to node or the node which has no children. The algorithm then backtracks from the dead end towards the most recent node that is yet to be completely explored. The data structure which is being used in depth first search is stack. In depth first search, the edges that leads to an unvisited node are called discovery edges, while the edges that leads to an already visited node are called as block edges. So if you see here in depth first search, the first branch will be called as level 0. The next branch is level 1, then consecutively level 2 and level 3. So there are 4 levels in this particular graph. So if you see depth first search, it will go deeper and deeper to all the levels, left side nodes of all the levels first. Then only it will go back to the other children of the previous levels. So if you want to search if G is the goal state, what will happen is from S source node, first it will explore to A, then explores to B, then explore to C, then explore to G. So once G is found from this path itself, while you are traversing the path in this itself, so you can just end the search. So the search path will be resulted on this particular searching is S, A, B, C, and G. How DFS is working is pick a starting node and push all its adjacent nodes to a stack. Pop a node from stack to select the next node to visit and push all its adjacent nodes into stack. Repeat this process until the stack is empty. Ensure that the nodes that are visited are marked. This will prevent you from visiting the same node more than once. If you do not mark the nodes that are visited and you visit the same node more than once, you may end up in an infinite loop. If you see here, this particular tree, A will be on the top of the stack initially, then A will be popped up and it will verify that whether it is a goal. No, right? So push its children on the stack. So A successors are pushed. So A successor is B and B will be on top of E. A successor are B and E, but the top will be pointing towards the B because it is the left side node as because it is the depth first search. Then pop B. Now we have to pop your B, whatever the stack is pointing, no, that should be popped up. Is it and we have to verify each and every time is whatever the nodes we have traversed, is it a goal or not? Now B is not a goal. So no, push its children on the stack. Now we have to push its B's children onto the stack. B successor is pushed. What is B successor? It is C. So C will be pointed by the stack. C will be the top of your stack. Now we have to pop what? C next. So while popping out the C, we have to verify that whether it is a goal or not. No, it is not actually the goal. What is our goal is a D. So if since it's not a goal, we have to push it children, that is C's children onto this stack. So C successor or children are pushed onto this stack and C's successor are what? D. So D will be pointed as the top of the stack. Now we have to see that whether D is a goal or not after popping it out. So pop D and verify that whether D is a goal or not. Yes, it's a goal and you can stop searching the algorithm and algorithm will stop and terminate. So where the stack is popped out nodes or stacked popped out nodes can be tracked in order to find the path from where the searching tree is starting and traversed and it was reached the goal state. So if you see the stack is popping out A, B, C and then D. So A, B, C, D will be the path to search the goal state to D from A. So this is how DFS will be working. So if you see this DFS algorithm step by step, if the initial state is a goal state, quit and return success. Otherwise, do the following until success or failure is signaled. Generate a success or E of the initial state. If there are no more success or signal failure. Call depth first search with E as the initial state. If the success is returned, signal success. Otherwise, continues in this loop. So what will happen is with respect to this example, step 1 initially node list contains only one node corresponding to the state A. Initial state will be A. So that will be in the node list that is added to the node list. So what will happen is A will be removed from the node list as we have discussed earlier in the stack with respect to popping out the nodes from the stack. Now A is expanded and children's are what? B and C. They will be put it in the front of the node list because it follows the stack. And then now B is removed from the node list as its children is D and E are pushed in front of the node list. So then what we have to do is node D will be removed from node list and C and F are its children. They are pushed into the front of the node list. Now we have to expand what? C. So C should be removed from the node list. Its child G is pushed in front of the node list. Then if G is the goal state, expand the G, okay, the G is pushed out of the expanded and G is the goal state. If you verify, then you can stop the algorithm and the path it was traversed to reach the goal state from the starting state A is A, B, D, C, G. So the corresponding path that has been searched through DFS is A, B, D, C, G. If we consider parameter analysis for DFS, that is time and space complexities and other parameters, completeness, time complexity, space complexity, and optimality, DFS search algorithm is actually complete within the finite space as it will expand every node within a limited search tree. Time complexity of DFS will be equivalent to the node traversed by the algorithm. It is given by T of B is equal to 1 plus B square plus BQ plus B power D. So which is nothing but a big O of B power D, where B is the branching factor, D is the maximum depth of any node. If you consider space complexity, DFS algorithm needs to store only single path from the root node. Hence, space complexity of DFS is equivalent to the size of the fringe set, which is O of B into D. So optimality, DFS algorithm is not optimal. That is, it is not non-optimum because generate large number of steps or high cost if the node is if the node is available in a infinite depth. So what are the disadvantages and advantages of depth first search? Advantages of depth first search are depth first search requires less memory since only the nodes on the current path are stored. And depth first search may find a solution without examining much of search space at all. So its time complexity is less and also space complexity is lesser. Disadvantage of depth first searches, it may find a suboptimal solution, one that is deeper or more costly than the best solution. About uninformed search methods, the first uninformed popular search method is breadth first search, and breadth first search follows the FIFO data structure. Okay, your uh, depth first search followed a LIFO data structure. Breadth first search follows a FIFO data structure. If you consider a FIFO data structure, again the node will start from A, and here first level by level, all the nodes on that particular level will be explored, then it goes to the next level. It will not search depth wise with respect to all the children of the particular node. Instead, it will go to the particular branch and all in the particular branch, all its children are explored first, then only it will go to the next branch or next level. So first A will be expanded, then B and C will be expanded, then B's children D and E will be explored, then C children F and G will be explored. And breadth first search is the most common search strategy for traversing a tree or graph. This algorithm searches breadth first in a tree or a graph. So it's called breadth first search. By breadth wise, it is used to search the tree or a graph. That is why it is also known as a breadth first search. So breadth first search algorithm starts searching from the root node of the tree and expands all successor nodes at the current level before before moving to nodes of the next level. The breadth first search algorithm is an example of a general graph search algorithm. Breadth first search implemented using FIFO-Q data structure. So if you consider breadth first search with respect to all levels, here if you take this tree, how many levels are there? Level 0, level 1, level 2, level 3 and level 4. So what will happen is first it will complete a first level 0 starts with level 0 with this source node, then it will go to level 1, then it will go to level 2, then it will go to level 3, then it will go to level 4. So how the algorithm step-by-step manner it works is, it's create a variable called node list and set it to the initial state until a goal state is found or node list is empty. Remove the first element from the node list and call it E. If node list was empty, then quit. For element E, do the following. Apply the rule to generate a new state. If the new state is a goal state, quit and return this state. Otherwise, add the new state to the end of the node list. So if you see with respect to the example of a breadth first search, here this is the tree that has been given. How the breadth first search will work here, we'll just see. First, the node list will be created. On the node list, first state will be added to the node list A. And then the step 2, what will happen is A will be removed from the node list. The nodes are expanded and the children are B and C. They are placed at the back of the node list because it follows the FIFO data structure. Then what will happen is B will be removed from the node list and it will be expanded. Its children are what? D and E. And then they'll be put back into the node list D and E. Then what will happen is D will be retained and C will be removed from the node list and it will be expanded and its children are what? D and G. Then they will be put into the back of the node list, that is Q. Now what will happen is we have to expand what is at the front of D. So we have to start expanding this D. So D is removed from the node list. Its children are what? C and F, and they will be added to the node list at the back of the Q, that is the node list. C and F are added at the back. Now which one we have to start expand? E. So E will be expanded. For expansion of it, we have to remove from the node list. But if you see that E has no children. So what will happen is next what is there in the node list we should see, that is D. So we should start removing D from the node list and start expanding D, and D children are what? B and F. They should be added at the end of the node list. So B and F are added at the end of the node list, at the end of the queue. So D is being expanded. And then what will happen is G is selected for expansion. It is found that what? It is a goal. Hence, the algorithm returns the path ACG by following the parent pointers of the node corresponding to G. So, if you see the time complexity, that is parameters, evaluation parameters of breadth first search with respect to time complexity, space complexity, completeness, and optimality. Time complexity of breadth first search can be obtained by the number of nodes transferred in breadth first search until the shallowest node, where D is the depth of the shallowest solution and B is the node at every state. So T of B formula will be what? 1 plus B square plus B power 3 plus B power D. So it's in general it is big O of B power D. So space complexity of BFS algorithm is given by the memory size of frontier, which is O of B2 power D. In fact, for depth first search, it is B into D. Here it is more by given order of B to the power D, because if at all to search any children node, it has to search all the nodes in the frontier before that node. So it will be almost searching all the nodes. It's equivalent to the time complexity. Completeness, BFS is complete, which means if the shallowest node goal state is at some point at finite depth, then BFS will find a solution. Optimality is optimal if the past cost is node of the is not greater than the depth of the node. And advantages and disadvantages. One of the simplest search techniques, it's complete. Is there any solution? BFS guaranteed to find it. If there are multiple solutions, then a minimum solution will be found. Disadvantages, it cannot be effectively used unless the search space is quite small. So about a blind first search, we will discuss in the next class. That's it for today. Thank you all for watching it.